So what are the thermodynamic considerations? Of these radical reactions? Well, we have our very familiar equation now. Gibbs free energy is equal to delta H minus T delta S. The delta S difference is going to be very small in these reactions because we have two reactants and they're making two products. So we don't expect the delta S to be very much. So the delta G is going to essentially be equal to delta H, at least for good enough for us. Okay, so we know, of course, that the delta H is equal to the energy of the bonds broken minus the energy of the bonds formed. And if we calculate a radical halogenation of methane, and using these numbers, we come up with fluorine having a delta H of minus 431. This is almost too reactive. Chlorine is minus 104 in the good range, and bromine is minus 33. So these are usable. And we find that iodine is just not reactive because it's got a positive delta G, and it will not work, not reactive. So bromination will occur because it's exothermic, but it's going to be much slower than chlorination. The first step is the rate determining step. And we're going to look at this more closely. The first propagation step's the hydrogen extraction. For chlorine, it's negative. So we see this distance here is our delta H, and that's a negative, and so that reaction goes quite well. For bromine, it's positive. So this is not favorable. However, because this is exothermic, the result of the reaction is that it will go. The entire reaction is exothermic. We just have this large hump that we have to get over in order to make it go. We're going to use this hump to explain the selectivity of halogenation. If you're going to add a halogen, you can remove the hydrogen from the end, and then you get this compound. Or we can remove the hydrogen from the middle. And as you would predict from what we've already talked about, the middle is more favored because the intermediate with a secondary is going to be favored over the primary. The first and rate limiting step is the hydrogen extraction, and developing the radical in this secondary position is more stable. We look at bromination, we see that instead of being, what did we say up here, it was 60-40, we've got 97% at the secondary position. So why the difference? Okay, so let's first look at these diagrams. We've got potential energy on this axis and the reaction coordinate. This first one is the chlorination. And you can see the reactants are here. This is our transition state. And this is just the initial step. This is the first step. And the reactants are closer to the transition state because this is exothermic. And down here we have a drawing. This bond that I'm drawing in green is just beginning to break. So this has little free radical character. Now let's look at what happens with bromination. So this is the bromination side, and it's also the first step. We're looking at the same hydrogen abstraction. Because this is an endothermic process, the transition state here is closer to looking like the intermediate. And the intermediate is this free radical that we have down here. This is a long bond we get, and it has more free radical character. Okay, so the transition state has more free radical character. This table up here is just a summary, I think, of what I just said. Chlorination, the first and rate-limiting step is exothermic. Because of that, the transition state is closer to the reactants. And so it matters more whether it's what kind of radical character it has. In bromination, it's endothermic. The transition state is closer to that of the intermediates, which is the radical. And the transition state has a high radical character. So this is going to be useful because if we do bromination, we can control where the halogen goes. This last set of diagrams, this is chlorination and this is bromination. This is the same step, it's the hydrogen extraction. And we're looking at the potential energy of the intermediate. And the potential energy of the intermediate doesn't matter a whole lot whether it's primary, secondary, or tertiary. However, when we look at bromination, we find that there's a great deal of energy difference between whether it's first, second, or a third degree radical. So the upshot of this is that fluorine is not very selective. And so, fluorine is too reactive, I'm sorry. Fluorine is a little selective and bromine is most selective. And so we tend to do more bromine reactions. So let's predict the major product obtained from bromination of these substrates. So what we're looking for here is something that's going to make, well, first would be a resonance stable radical, and second would be a tertiary radical. I don't see any double bonds, so I don't think we're going to have any resonance in any of these. So we're looking for something that's going to make a tertiary radical. All right, so let's start off here. If we put a radical here, or here, or here, it will be primary. Now that's not going to be good. We can't do that. If we put a radical here, or here, here, or here, it's going to be secondary. And there is no hydrogen to abstract there. So that's a no-go. So we're going to end up putting our hydrogen is right here because that will give us a tertiary. And I'll put it a different color. We'll put it, not a hydrogen, it's bromine. Sorry about that. We were taking off a hydrogen. Okay, so we'll do the same thing here, and we will get, draw this. If we put our bromine in this location, that will give us the most stable intermediate. And this last one, see. Not sure I'm going to get all my methyl groups on this. It's got lots of methyl groups. Okay. We can't put one here, we can't put one here, can't put one there because there's no hydrogen to abstract, but we can put one right there. And that's where we're going to put her. And that's the end of this section. Next we'll be looking at the stereochemistry of these reactions.